a new topic. We're going to define the stress tensor. And the stress tensor is a measure of the load experienced at a single point in a material. Okay, so first we have to talk about this idea of the load that's experienced by a point in a material. How many people took, when you took statics, how many of you did internal loads and beams? Did pretty much everyone do that in statics? Where you're calculating the bending moment, the tension, and the shear force? No. Okay, I'm going to go through all that again. But as just sort of an introduction to that idea, think about flexing a pencil between your hands. Okay, so well, that's a pretty long pencil. But it's a crazy novelty pencil. If you kept doing that until it broke, where would it break? Okay, well, first, what's a free body diagram? So a free body diagram of that pencil or that stick, you could think of as something like the fingers would be pulling down here, the thumb would be pushing up, and it's symmetric, so you'd have something like that over there. And maybe we'll call that R1, R1, R2, R2. Okay. So from the free body diagram, you would think, well, one of these four spots is where it's going to break, because that's the only place that there's loads. I mean, if you were asked just from looking at the free body diagram and you'd never bent a stick or whatever, you'd say, yeah, I guess it must be one of those four places. But it actually won't break at any of those four places. It'll break somewhere in between the two R2s. Okay. So it doesn't break where those external loads are applied. Instead, it breaks in between the thumbs somewhere. So what's going on? How can you measure how likely this thing is to break if whatever makes it break doesn't show up in the free body diagram? Okay. So what makes it break? And the answer is at every point, there are loads applied to the material point by the surrounding material that keep that point in equilibrium. And when the load required for equilibrium exceeds what the material can produce, then the pieces, accelerate, and that's what a fracture is. So to see when something's going to break, yeah, question.
Is it kind of like friction, like how if you push something that doesn't move, why would you make it faster?
Yeah. So let's see. You maybe more than friction. I mean, so what would it take for like the wall to break? Like that wall keeps. So I barely put any force on it, and the wall puts an equal and opposite force into my hand. Well, I guess it's not really friction. I mean, it's we'll talk about the directions and stuff of those forces in a little bit. But really, just think of it as like, okay, here's a better one. So think of a material, instead of a material, think of a bunch of people like trying to hold their hands clasped together, and you have two people pulling on you have someone pulling on one side and someone pulling on the other side. The line of people isn't going to break where you're applying the force at the outside. That's equivalent to like the external load. What's going to happen is eventually, if you apply enough force to this arm, somewhere in that line, the people's hands are going to unclasp. So as you're pulling on the outside, the forces required for them to stay together get bigger and bigger until they can't hold onto each other's hands. And at that point, they let go and it breaks. And that's what happens with material too. So it's not really directly to measure when something is going to break. You don't want to measure the external loads applied to it. You want to measure what are the loads that the material has to apply to itself at different points in order to keep it from breaking apart. And that's the idea of stress. It's also the idea of internal loads in beams. Okay, so think of a material. And say we want to measure the internal loads at this point. Okay, how are we going to do that? So we want to calculate the internal loads at the point shown. And what are the internal loads? Those are the loads that's applied to that point by the surrounding material. Okay, so what we're going to do is define a cube that surrounds that point. And ask yourself, what are the loads applied to that cube by the surrounding material? Okay, well, thinking about it like statics. So here's the cube. And that cube is surrounded by material that's connected to it. So what kind of joint would you say there is between each one of these 6 faces and the surrounding materials? Like a ball and socket joint, a pin joint? What kind of connection is there between this cube and what it's connected to? Well, it's a fixed joint, right? I mean, it's like welded to it, so that thing can't go anywhere. So on each one of these faces, do you remember what kind of loads does a fixed joint apply to an object? So it applies in 3 dimensions. It applies 3 components of couple and 3 components of force, right? So on each one of these faces, there's a force vector like that, and a couple vector like that, and that's true on all of these. Okay, and so how many variables worth of loads have I shown there? So I've shown 3 faces, and each one has 6, right? So that's 18 total load components. But what I haven't shown is the negative sides of all those. So 3 sides are hidden. And so that means that 36 total load components. right now we're thinking that to represent the loading on that point by the surroundings, it takes 36 values, okay? The stress tensor, what we're going to end up is with 6 values. We're going to keep analyzing this, and each thing that we think about is going to eliminate the independence of some of those variables. Okay, well, the first thing is so like I said, this reduces to 6 independent values. And that's the stress tensor. So how does that work? Well, first, if you have forces acting all over this big object, do you think those loads would change depending on the size of that box? If you stretch this box out all the way to the surface, those loads would be one thing. If you made it really small, it would be something else, okay? Depending on how big or small you make it, you're representing either, a big volume worth of points or a small volume worth of points. We just want to represent this one point. So it makes sense that we'd want to calculate this in a limit as you shrink that box down to 0 size. Okay, so the first thing is we want the limit as the box size goes to 0. Well, that would make the forces in the couples go to 0 too, though. So that would make the forces and couples go to 0. So instead of thinking of forces and couples, let's think about force per unit area and couple per unit area. The forces per area don't approach 0. Okay, so that worked out just the way we want it to. These do approach 0. And so if we think of this internal loading as the force per area and the couple per area, we can forget about all of those 18 couple values, okay? So let's say we're only measuring the force per area. Okay, so let's draw this infinitesimal box. And now we have components like this, and this, and then all the faces that are obscured. So now that we've gotten rid of all the couple stuff, and by the way, the reason the couple per area goes away is because the force per area approaches something finite, but then to calculate the couple, it has to do with the length, the distance the forces are apart, and that's also shrinking. So this shrinks with another, it has another order of size that's shrinking as the size goes to 0. So it goes away. And so now how many total values are we down to? So it's showing 3, that's 9. It's hiding all of the 3 other faces. So now we're down to 18 total load values. Okay, so that's what we did with the first step. Then the second step is the fact that we are requiring this point to be in force equilibrium because it's not accelerating. Requires that the forces on opposite faces have to be equal and opposite. Okay, well, that means that we've eliminated the independence of any values on those 3 obscured sides. So now how many values are we down to? 9.
So we just ignore the opposite force.
Yeah, we're just trying to figure out how many values we have to keep track of. Okay, so yeah, they're there, but we don't have to keep track of them because we know they match the ones we're keeping track of. And then the last thing is it also has no angular acceleration. And that requires that if you're looking straight on any face, any force along the surface like this, well, we already figured out that the opposite has to be that. But that would be producing an angular acceleration, right? And the only way to not have an angular acceleration is to have a force going that way that's the same magnitude as these two. And equal and opposite says that that one has to be opposite. Okay. And that eliminates 3 more required values. And so this leaves us with our final 6 independent load values. Okay, so let's look at the naming for those. So these 6 values are the stress tensor. We haven't discussed the format of it yet, but these are the values that we're going to be keeping track of to represent how much internal loading there is at a single point. Now here are the elements of the stress tensor. If we're using a coordinate system like this, where that's x, that's y, and that's z, then there are forces like this, this, and this. On each face, there are forces in the direction of every axis. But we only need to represent these three faces. Every element has two subscripts. The first is the face that you're on, and the second is the component. Okay, so this component, so to think about what face you're on, you want to think about which axis is pointed from the inside to the outside of that face. So this face, let's do this one first, okay? Which of these three axes, if you started on the inside, would point out of that face perpendicularly? X, yep, so that's the X face. So this element is the X face, and then what axis is it in the direction of? So that's the XX stress. Then this one here, it's on the same face, so the first subscript is still X. But what axis is that in the direction of? Yep, so that's XY. What's this one called? XZ, yep. And then on this one, what face is this? Y, so this is sigma Y, and what direction is it? Y. This is sigma Y, in what direction? Yep. Dang it. And this one is YZ. And then this is the Z face. This is ZX, ZY, and ZZ. That's 9 values, but the requirement to prevent angular acceleration says sigma XY is equal to sigma YX, sigma XZ is equal to sigma ZX, and sigma YZ is equal to sigma ZY. So this stress tensor is represented by this 3x3 matrix. Sigma XX, sigma XY, sigma XZ. Symmetry says this is XY again. YY, YZ, XZ again, YZ again, and ZZ. And this thing is called the stress tensor. It has units of force per area. And so the SI units are newtons per meter squared, which is pascals. It's units of pressure. There is always a relationship that you have to remember. Let's say it's an equivalence. Between the stress element, or I'll call it the stress cube, that shows the external loads acting on a point, external, so the external loads acting on an infinitesimal cube surrounding a point, and the stress tensor. And the relationship looks like this. So here's the stress cube. And each one of these faces has 3 components of force per area acting. This one's called the XX stress, XY, XZ, and then this one is the stress YX, but we know from symmetry that that's equal to XY, sigma YY, sigma YZ, and then on the Z face, we have sigma ZX, sigma ZY, and sigma ZZ. Okay. And those are equivalent. Those tell the same story as the stress tensor, sigma with an undersquiggle, sigma XX, sigma XY, sigma XZ. Now we'll use the symmetry. So this is XY, then YY, YZ. And then we'll use symmetry for the next 2. So sigma XZ again, sigma YZ again, and sigma ZZ. Okay, and the units for all of these values are force per area, which are also the units for pressure. And so the SI units are pascals. Diagonal elements are called normal stresses. Okay, these are the normal stresses. So what does it mean that those are the normal stresses? Well, it sort of makes sense if you look at the stress cube. What's special about those 3 and the diagonal? That's right. They're all normal to the face that they're acting on. So the diagonal elements are the normal stresses. And each is perpendicular to the face. The off-diagonal elements are called the shear stresses. And they act in the plane of the face.